next few minutes, we will show an overview of how Ansys can help you design electric motors in a logical flow, from initial design all the way to fully coupled electrical, thermal, stress, acoustics, and drives. Ansys provides a complete design flow that progresses from analytical design sizing options to rigorous electromagnetics design to fully coupled electromagnetic, thermal, stress, and acoustic physics modeling. Finite element analysis of the electromagnetics is the foundation for creating physics-based models that are used with 0D systems models. And the Ansys workbench can be used to manage multiphysics design and perform system-wide optimization. The first step in the flow is to apply the Ansys RMExpert design sizing tool. RMExpert is a template-based electrical machine design tool that provides fast analytical calculations of machine performance to allow engineers to zero in on an appropriate design. You can select from many motor types and create custom designs to your specifications quickly. It then creates ready-to-solve 2D and 3D models for detailed transient finite element calculations in Ansys Maxwell. Maxwell simulates 3D and 2D electromagnetic and electromechanical devices using the most advanced modeling technology. Maxwell uses an automated finite element method to solve static, frequency domain, and time-varying electromagnetic and electric fields. For motors, we have the most advanced modeling methods for laminations, nonlinear materials, temperature-dependent demagnetization, hysteresis, magnetization processes, and core loss. Here you see an example that required the most advanced magnetics modeling. This hysteresis motor has a solid rotor with a thin layer of ferromagnetic material that provides dynamic magnetic pole creation. This can be modeled only if the ferromagnetic material demonstrates hysteresis. Accurate prediction of motor efficiency also requires nonlinear modeling and eddy effects. A measure of accuracy is the power balance between electrical input power and the mechanical output power, including various losses. High-performance computing speeds the solution of electric machines. Ansys Maxwell can use parallel computing to speed 3D transient simulations. Here you see transient simulation of a large permanent magnet machine using parallel computing. The bar chart shows 5 to 6 times speed up and excellent scaling using multiple cores. We've also sped up the transient AC steady-state solutions. Here you see an induction machine that reached steady state 24 times faster using an advanced new algorithm. Electric machines require appropriate electric drive circuits. Maxwell finite element analysis co-simulates with the Simplorer circuit simulator to evaluate how nonlinear behavior of the motor affects the drive circuit and vice versa. Ansys tools allow you to simulate complete integrated motor behavior by linking physics and systems solutions. RMExpert provides the initial motor design and 2D and 3D models. Maxwell performs 2D and 3D electromagnetics analysis. Ansys CFD and Ansys Mechanical are used for thermal and mechanical stress, and Simplorer ties all the physics together in a top-level system for drive circuits and other behavioral components. We now show you how you can use the integrated motor solution to meet common design objectives such as reducing weight and size of the motor, reduce the size of the magnets to save cost, improve efficiency, and reduce the torque ripple. Ansys has created an electric machine design toolkit to address the challenges. Automated scripting built directly in the Maxwell interface allows you to set up efficiency map calculations and compute torque speed curves and efficiency maps automatically. An intuitive displayer is included with the design kit. A simple pull-down menu provides you immediate access to many maps, including efficiency, current, voltage, power factor, core loss, and many others. Here you see a Maxwell 2D simulation of the Toyota Prius motor. We have used the toolkit to calculate the efficiency map. Simulation results show excellent agreement with measurements. The motor was simulated using the same maximum current and voltage limit as was used in the measurements. Each operation point was simulated in the time domain to obtain the efficiency map using frequency-dependent core loss coefficients. For the final example, we show comprehensive multiphysics simulation of an electric machine. This flowchart depicts the process whereby electromagnetics is used to drive thermal simulations, stress analysis, harmonic analysis, and finally acoustic noise. The mapping functions that you see are handled automatically in the Ansys workbench environment. The first step is electrothermal design. Maxwell is used to simulate electromagnetic fields and the associated electromagnetic power loss density. Automated routines map these losses to the Ansys CFD, computational fluid dynamics solver, for static or transient thermal simulations. The resulting temperatures from the thermal analysis can be passed back to Maxwell to adjust material properties so that additional corrections to the electromagnetic field may be computed. The next step is electromechanical design. In this case, we map the electromechanically induced forces to a finite element stress analysis in Ansys Mechanical. Again, automated procedures in Ansys Workbench streamline the process. The mechanical stresses deform the geometry, and the deformed mesh information can be passed back to Maxwell for further electromagnetic simulation. For the final analysis, we pass transient electromagnetically induced forces to structural dynamics simulation in Mechanical to compute structural harmonics. Those harmonics change the shape of the stator, which in turn produces an acoustic field as computed by Ansys Mechanical. As you can see, this approach can be used to predict acoustic noise, and hence enables you to apply strategies to reduce that noise. In this video, we introduce the Ansys electric machine design flow that covers initial design to electromagnetics with multiphysics and systems. We have developed the most advanced modeling technology so that you can predict motor electromagnetic behavior accurately. Automated tools produce efficiency maps and torque speed curves and even provide you with optimal operating points. We showed you how you can use the multiphysics coupling analysis to predict thermal behavior, stress, and acoustic noise. Thanks for watching.